Okay, so let's have a look. I'm going to show you some really good math tricks today. It'll be useful to you in here, but other places too. So let's look at a couple of these kinds of problems that we talked about on Friday. Stuff where we can make them simple, right? Because it's not really telling us, I mean, how could we do these problems? Let's just talk about a couple strategies. We got a steel ball attached to a string. We're swinging it around in a horizontal circle at a constant rate. Then we tweak things. The mass is then reduced to 1/4 of its previous value, but the radius and period remain constant, remain unchanged. And so we want to know what's the new velocity and what's the new acceleration and what's the new force. So we could make this difficult. We could use these equations, and we could even like plug in some sample values or something weird like that. We make up some values and then just don't change them, and go through and like solve for velocity in terms of the other stuff. But that's a lot of work. We don't need to do that. What I want to show you here is that we can just use these relationships. In fact, we really can just use the proportionalities. We can just get rid of everything that's going to be constant and just focus on the way that the variables change, right? That the important physics quantities change. Like, so for example, in part 1 here, now we know that, let's look at, and let's mark in red everything that's changing, and maybe let's mark in green everything that's staying constant. How about it? Okay. So the mass is changing, right? So mass is changing. The radius and period are staying the same, right? But in the first one, we want to know how much the velocity has changed, right? So the velocity is changing also. So then what's going to be, we want to find one of these relationships, right? And these are all the relationships we have that relate centripetal acceleration to other uniform circular motion stuff. Or the other one is the one that doesn't really involve doesn't involve centripetal acceleration, but it relates speed to radius and period for circular motion, right? So we got essentially these 3 different relationships. Which one do we want here if the things that are changing that we want to keep track of are m and v? Well, does m even show up in these? No. I guess we need maybe one more. What's the definition of any net force by Newton's second law? F equals ma, right? So we could add, for the purposes of this problem, at least for that first part there, we could say, okay, we got one other one. Centripetal force equals m times what? Acceleration. Yeah, centripetal acceleration, right? So in that equation, let's see here. So we can see that the mass, the acceleration and the force and the mass are going to be related by that one, right? But velocity doesn't show up there, right? So what we can do is we know that acceleration is going to be related to force, right? Okay, so we're going to come back to this one in a little bit, but for now, we just want to say, okay, let's relate the acceleration to the velocity then, how about? Okay, does that make sense? So if the mass is changing, what's going to happen to the velocity? Any idea? Does this make sense? If I move this guy out of the way, does it make sense that it's not changing? Because look, if I look at any of these velocity equations, does mass even show up?
If the period remains the same, the radius is the same, the velocity is the same.
Right, right. And so we can see that radius and period are staying the same, right? And so if radius, that's another way to look at it. If radius and period are staying the same, then doesn't velocity have to stay the same? See what I'm saying? Okay, here we've got a relationship between velocity and radius and period. Well, if none of those things are changing, then this won't either. But beyond that, m doesn't even show up in any of these things, right? So the mass is going to have nothing to do with velocity. Okay? Make sense? Here's kind of the trick I want to show you. If we just grab something like this guy. Oops.
What does that symbol mean?
That symbol means proportional. That symbol where it's kind of like a circle, it's just like almost like an infinity with a piece taken out. Yeah, it means proportional. And so what does it mean to be proportional? Whatever happens to this side has to happen to this side. They They have to grow and shrink by the same amount always, right? Things are proportional. So if those are proportional, where did we get that from? Well, really, it's just this equation up here if we just take away the 2 pi. But the 2 pi is constant. It's never going to change, is it? So this is a much easier way for us to deal with this. We can use this relationship right here, and we can turn this into a much easier equation to deal with. So we said that V is changing, R and T are staying the same, right? So then if something is staying the same, that's equivalent to multiplying it by what number? 1. Okay, so then we could replace, in this proportionality, we could rewrite this as an equation where instead of R, we're just going to put in the factor by which it's changing. Instead of T, we're going to put in the factor by which it's changing, right? Now we're asking about V. Well, what would V have to be in order for it to change by the same amount as the right side? It's got to be 1, doesn't it? See what I'm saying? So V has to be changing by 1. It's not changing at all, right? It can't change because neither of those changed, and this has to be the equation that relates those two, right? Or that proportionality. Okay, so that has to be 1.
So,
Okay, so question. No, question.
I was gonna say, so if 2 pi changed, but 2 pi can't change.
2 pi can't
Yeah.
change because 2 pi is just a number, right? It's a constant. By definition, it will never change. What about acceleration? Well, how is acceleration related to some stuff that we know? Let's see, like radius and period. It's right there, isn't it? So we could use this guy. For part 2, we could take this one. I'll just drag it down here, how about it? So we're going to use this one, and we're going to turn that into an equation, right? Where we're just going to look at how each of these quantities would have to change for that to remain proportional, right? And all we've done is we've just taken out the 4 pi squared because it's never going to change, right? So R doesn't change, right? So that's equal to 1. T doesn't change, right? So therefore, does T squared change? Okay, if T's not changing, T squared doesn't change. That's also equal to 1. So then, what does A have to be? It's got to be 1, right? It can't be changing. Does that make sense? Okay, and it is. Okay. Well, now let's look at part 3. Okay, part 3, it says the force acting on the ball is changed by a factor of what? Okay, so we know that acceleration is equal to, it's not changing, right? We said that one was equal to 1, right? And so we can now take this equation right here. So we know that acceleration is 1. Mass, though, what about the mass? The mass is being reduced to 1/4. So what's it being multiplied by? 1/4, right? Because it's being changed to 1/4 of its previous value, right? So M is not constant. That's red, and it's a 1/4. So what does the force have to be doing then to stay the same as this other side? It's got to be 1/4, doesn't it? Make sense now? Okay, isn't that a great way to look at it? So you can just see that. How are we going to keep this thing in balance, right? It's got to stay proportional, right? Make sense? Okay, let's try another one. Make sure you got this figured out. Try this guy. So you think about this for a second and tell me, let's just do part 1. So look at what's being changed and what's staying constant. Say it again.
Can you underline them with the red ink?
Yeah, sure, let's underline. So you tell me, I'll circle the things in red that are changing. So what's changing? Period. So the period is being quadrupled, okay, increased by a factor of 4. In part 1, we want to look at how the velocity is changing. And we don't know if it's changing, but we'll assume it is, right? We'll find out. What's being held constant?
Radius and mass.
Radius and mass. Okay, so what's a relationship then? Which one of these relationships is going to relate period and velocity and radius? second. Period and velocity and radius. And the mass doesn't show up in any of them, right? So that's not a kinematic quantity, but that's that one, isn't it? Everybody agree? Velocity, period, and mass. Okay, or excuse me, period and radius, right? So we can use this one. Right, so for part one, that's the equation we're going to use. So then we end up with V equals R over T. So let's fill in the blanks. Which one is being held constant? R is, right? So then R is going to be 1. What do they tell us? The period is being quadrupled. So what's T being multiplied by? 4, okay. So we got to have a 4 on the bottom. So then what's going to happen to V?
1/4.
Yeah, how about that? It's got to be multiplied by 1/4. It's going to be reduced by a factor of 4, right? And voila, there it is. Okay. All right, how about, let's look at part 2 now. In part 2, now we're not talking about velocity, we're talking about acceleration. So now we want to go back and say, we're not really worried about velocity. Is there an equation that relates acceleration and period and radius? That looks like the number 2, doesn't it? The middle one, right? So we'll use the proportionality.
Although, wouldn't you also be able to use the first one?
We could, because now we know what V is, right? We know that V is 1/4, so we could use that information and use the first one too if we wanted to, right? That'd be fine. What about this guy? So this one's telling us, let's see, we're going to fill in these blanks, right? This is the relationship we're using. Okay, so it says period is being quadrupled. So then what's happening to T squared? 16, isn't it? So this is going to be a 4 squared, right? Makes sense?
Oh, okay.
See what I'm saying? Because that's being squared. Okay, T is changing by 4. R is remaining unchanged, right? So what's that one going to be? 1. And so then what has to go on this side?
1/16.
Yeah. That's got to be 1/16, doesn't it? Right? And there it is. What do you know? Okay? And then the last one's the easy one. That's just F equals MA, right? So the bottom one is just going to be, now we know we've got centripetal force equals mass times centripetal acceleration. What do we know? Centripetal acceleration is 1/16, right? We just figured that out.
Mass is 1.
The mass is staying constant, so that's 1. So then what is,
150.
yeah, it's got to be 1/16, right?
Wow.
See how that works? Okay, try this one all on your own. Okay, what do you think? What's changing? Yeah, I'll just underline some stuff. Or circle it. And period, right? That's one. What's staying constant, mass, velocity? Okay, so Jonathan, what am I gonna use then? If I wanna relate R and T, and I know probably V also, right? V is constant. So R, T, and V, which one's that gonna be? Okay, this guy.
Yeah.
So we'll grab, that's the relationship. Which means I've gotta fill in blanks. Okay, so what do we know?
Velocity is one.
Would it be smart to do acceleration first?
I mean, you could, it'd be fine, and
Because
you could. So suggestion is you could do like
you could do the first equation.
first equation,
since
and then
radius is
use
one.
that one to solve for, right? Yeah, that's possible, sure. So what do we know? We know velocity stays the same, right? So that's gotta be 1, so this is a little different look this time. What about radius? What's it telling us about radius? It's cut in half, and we're trying to solve for t. So what does it have to be then for that to be a true equation? 2. No. It's gotta be a half. Right? Because if I want the answer to be 1 on the left side, that means I have to divide something by itself, right?
Yes.
Okay?
It's not.
Okay, did everybody see that? Right? If that's gonna stay the same, then for the right side to stay the same, I've gotta have the same thing on the top that's on the bottom, so they'll cancel. And that makes sense. When I divide by a fraction, I'm really just multiplying by the reciprocal, right? Flipping and multiplying. 1/2 times 2 would give me 1, right? And voila. That's what we got. Right? Okay, so what about the next one then? Okay, so we could use, now we know what, well, we know V and R, don't we? Yeah, so we could use this guy, right? Okay, we just need to fill in blanks here. So we've got something equals something over something. Okay, so we said V was 1, right? So then up here, this is just going to be a 1 squared, which is 1. R is 1/2, we know, right? So this guy is 1/2. And so then what does that mean centripetal acceleration needs to be? You got to think about this one.
Would be 2.
It's going to be 2, isn't it? Yeah, it's because it's got to be equal to this side. Well, we would just have 1 divided by 1/2, so we flip and multiply, and we're going to get 2. Okay? Okay, and then last one, F equals ma, the mass is staying constant, so doesn't it make sense that, I won't even write this one down. What's the answer going to be? 2. It's got to be 2, doesn't it? Because the mass is staying the same. And so force and acceleration would have to change by the same amount. Okay? Last one. Let's go through this one pretty quick. So let's see, velocity is tripled. We're going to look at how the radius changes when the period and mass stay the same. So once again, I guess we go back to this guy, don't we? Right? So we get something equals something over something. What do we know? Period stays the same. So that's 1. The velocity is tripled.
So it's 3.
So that's going to be 3. So what's that have to be?
3.
Yeah. So R has to be 3. Okay, how about acceleration? Well, we're just going to go back to the first one again, aren't we? Right, so oops. So that gives us something equals something over something. So what do we know here? V is, what did we find V? V is 3, right? We found V is 3. So this, what goes here then?
9.
Ah, okay, good. 3 squared, good. R is 3, right? So what's the centripetal acceleration got to be? What's 3 squared divided by 3? 3. What's supposed to be a question mark? So that's going to be a 3, right? And then last one, what's that going to be? Okay, good. You got it. All right. So what about this guy? Let's look at a couple of questions then, beyond just some actual physics questions where we have to do some stuff. So how are we going to talk about this one? This is where, really we need to probably go back and spend a little more time on this.
Yeah.
You're going to find these aren't too bad, but we got to really kind of think about this here. So racing on a flat track, a car going 31.4 meters per second rounds a curve 60.4 meters in radius. What minimum coefficient of static friction must exist between the tires and the road for the car to make the turn without slipping? Okay, so seen from above, this guy's just going in a circle, right? What if I draw a free body diagram? So for our free body diagram, the car is just going to be represented by a point. How about? Okay, so here's the point.
You want to use your circle too?
Not really. I want to do something a little different. So we know this guy's going in uniform circular motion, though, right? So I'm going to say that means it's going to be rotating around some central. There's going to be a line of symmetry through the center of the circle, right? And it's just going to be going around that thing. Agreed? Okay, so let's take this to be the line of symmetry. And then what's that going to look like? Well, this guy's just going to be making kind of a circular path. Like that, right? Say it's going around in that direction. Everybody see what I got there? Okay, kind of a perspective drawing a little bit. So then this is the point that's maybe in the plane of the circle. Okay, so I could even draw something like I wanted to put, like we could even make that maybe like the x-axis or something, right? Maybe this is the y. See what I'm saying? You get the idea? Okay, so then if that's the case, what are the forces acting on the car? So gravity is definitely acting. Okay, so we've got, remember in this, we're just going back to our free body diagram, right? Where we just want to write down all the forces as vectors. So we've got its weight, mg, pushing straight down. It's a flat track, isn't it? Okay. Now what else? So the normal force is pushing up. Anything else going on? Yeah, there's got to be some friction. If there's not friction, this is a pretty simple problem. Then this is like what would happen if the guy was driving along in a straight line and there's where he wants to go, but if he crosses some ice covered with WD-40, there's no friction, and so he ain't making that turn. He's just going straight, right, into the border, okay? But there's got to be some friction in order for him to make the turn. In fact, what's the force that's providing the centripetal acceleration here?
The wheels.
Well, the friction, right? The friction is what's going to be pushing him inside towards the center of the turn, making him go in the circle, right? Okay, and if we look at this from a slightly different perspective, so now maybe I will use my circle tool. Okay, so if he's going in, he's going in that direction when he hits the turn, right? There has to be, at this point, he can be traveling along, and it doesn't matter if there's any friction, does it? For all we know, seen from above, he could just be sliding down the freeway with no control, but it'd look the same to us, right? If he's traveling at constant speed, that or traveling with cruise control, right? But when he gets to this turn, then all of a sudden he does need a force, because if he's going to make this turn, and that's the center of the circle, there has to be some centripetal force pushing him towards the center of the circle, right? How much centripetal force? Well, that much, right? So the acceleration is given by that. Okay? All right, so we can add one more thing then. We can add our static frictional force. And why is it static? He's moving.
Because each tire's on the tire.
Oh, okay, the tires aren't sliding. The tires are rolling, and so they're not sliding on the pavement, right? So it would be static.
Wouldn't we have two friction values, one from static and one from?
Okay, true, but now let's think about this. Let's go back to our picture here. Some good physics going on here. So if he's driving along and he's going to need to have a certain frictional value in order to be able to make this turn, right? Well, let's say there's not enough friction. If there's not enough friction, right, what's he going to do? Well, maybe not straight, but he's going to start sliding, right? Okay, so if he's sliding, even if he's able to somehow turn the car while he's sliding, which he wouldn't be able to do, but assume he could, there's still a problem here. Which is a stronger type of friction? Static or kinetic? Static is, right? Static is always going to be stronger, and so if the static isn't enough, the kinetic is not going to be enough for sure, right? So it would have to be static or nothing. Make sense? Okay. So then, here's our free body diagram. Pretty simple, really, right? So now let's break these up into, instead of x and y, we really don't want to break these up into x and y when we're talking about centripetal motion. We're going to talk about the motion as either being centripetal, so it's pointing towards the center of the circle, right? Or tangential, meaning it's traveling tangent to the circle. Seen from above, here would be those directions, right? We'd have so here's our car. That's one direction, and we're going to call that the centripetal direction, okay? And then that would be the other direction, and we'll call that the tangential direction. Now, it's going to be different up here, right? At this point right here, but we can still call them the same thing. That's tangential, and that's centripetal, right? Make sense? Okay. So then, right here, what are our equations of motion? So what's going to be the let's say these would be, and actually, I'm sorry, I kind of messed that up a little bit. These aren't really tangential, they're just vertical, right? So those are in the y direction, right? And when the guy finds himself over here, he's still going to have the same things going on. He's still going to have a green vector, a normal force vector pointing straight up. He's going to have a weight vector pointing straight down. But now in what direction is the friction going to be going? Kind of towards the center, still, centripetally. Does that make sense? So I didn't really mean to say tangential is a bad way to think about it. Think about it as being vertical forces, and then the horizontal forces are always going to be towards the center of the circle, right? So the net vertical force is given to us by the sum of what two forces? Which one's positive? Not natural, the normal force. Okay, so the normal force is the positive one. Which one's negative?
Gravity.
Wait,
Right? That's pointing down. And what do they have to equal probably?
Zero.
Gotta be zero, because it's not accelerating vertically, right? So there's one equation of motion right there. Okay. What about the centripetal component?
oh, the centripetal force and the friction
Yeah, well, in fact,
cancel each other.
okay, centripetal force, I think, is centripetal force a specific force?
No.
It's not really, it's just a brand, it's just a category of force, right? It could be, let's look at a couple different situations. In this situation, the centripetal force is being provided by the friction with the tires, right? But what if I had let's say I had a marble spinning around on a string? Now it's providing the centripetal force. Well, okay, and the string, the tension in the string, right? So the tension in the string is pulling the marble towards the center, so that would be providing the centripetal acceleration. what if you are riding on that gravitron thing? What's providing the centripetal force there when you're flattened against the outside and it's going in a big circle? Yeah, the pushing force of the wall, right? So in that case, it's actually the normal force, I guess, right? Pushing you towards the center of the circle. So centripetal force can be any number of different things, but what it really means is just whatever the force is pushing you towards the center, right? So then, what's the net centripetal force? What's the only force acting centripetally?
Friction.
Friction. So the static frictional force is pointing towards the center of the circle. Obviously, nothing is pushing towards the out. Nothing's pushing out, right? There's only a centripetal force pushing in, and so that must equal what? Not 0. Can't be 0 if he's going to go in a circle.
1.
It's got to equal. What's our formula for centripetal force? Well,
or acceleration.
M times, exactly, it's going to be mass times, it's going to be MA, but this time the A is centripetal acceleration, right? So that's equal to
There's 1/4 squared over R.
that,
Or over.
right? And so all we got to do then is just solve that system. We've got these two equations. Well, what's our formula for maximum static frictional force? It's always the same, right? Frictional forces are what?
Equals mu K.
Okay, mu sub s this time, times normal force, right? So this is just telling us mu sub s times normal force equals ma sub c. But what's normal force going to be from the first equation? Yeah, it just equals the weight, doesn't it, from equation number 1. So then we can rewrite this as mu sub s times, this becomes mg equals m times a sub c. Well, what can I do to the m's? Cancel.
So it's
And-
divided by G.
There it is, right? So centripetal acceleration, which is what we're trying to find here, what the coefficient of static friction must be, right?
So you just need 3.145 by 5.8.
Okay, right. So we know all the stuff that allows us to actually calculate what the necessary centripetal acceleration is. In fact, there's our formula right there, isn't it?
Why not just use that one?
Right? Well, okay, we can, but then we still need to be able to, what are we trying to solve for? We're trying to solve for mu, right? So if that's what we're trying to solve for, I got to get it by itself. So mu sub s is going to end up being centripetal acceleration divided by g. That kind of makes sense. In a way, if you really think about that, the necessary coefficient is going to have to be related to how much centripetal acceleration I need in comparison to gravity. How much is pushing me onto the ground, right? That kind of makes sense, maybe in a way. Yes?
When I did it, I thought like 1.98. That doesn't really make sense.
That does. That's the coefficient, right?
Yeah, for the coefficient.
You got something bigger than 1?
Yeah.
Well, boy, that would be pretty big. Yeah, that would be, I mean, it's possible that the rubber, tell you what, let's pick this, finish this one up and start a class tomorrow and see what happens. Did you have it right handy right there? Hey, let me know if you have it, let me just look at it real quick.
Yeah.
Okay, so you had 30, those are the numbers, 34.
Mine was 37.4 and 71.8.
Okay, so those, you were putting in those numbers right there?
Yeah.
Okay, so, right, so v squared over r, so you would have gotten, say it again,
I got 37.4
squared over 71.8, 19. Oh, yeah, that's gonna be, right.
So
So it would have to be, you'd have to have really sticky tires that would actually be like adhering to the ground. What's that term?
it'd be 1.9.
So we'll see that.
Yeah.
That's right. Good. Okay, so now that's what the physics tells us. Do you think probably you're able to make that turn then?
No.
I mean, it's unlikely. Very unlikely. So that tells you something important.
No.
That's what it would have to be.
Yeah.
Okay. Yes. I will sign that for you. So. Did you? Okay. Okay, yes.
It's not.